Section 5.3, the fundamental theorem of calculus, and there's actually two parts, part 1 and part 2. Well, so for the last few lectures, we have discussed the geometric interpretation of what the antiderivative is. Well, in this case, we call that the integral. And what it does is essentially calculate the area under a curve f of x between the limits a and b. All right, so, however, there's only two things that we have done so far. Number one, calculate or compute antiderivatives. That is, finding the inverse of the derivative using the antiderivative formula. You know, in this way, in a way, do the reverse of the derivative. You know, at the beginning we were finding, we were looking at this. What's it called? Thinking of what function could have a derivative to be, you know, has a derivative equal to the antiderivative. You know, that's what we were looking at first. But well, then we got to the actual formulas to find antiderivatives, and then we did calculations of these areas under those curves. However, we did that the ugly way, you know, the limit definition way. In just the same way, we got some derivatives using the limit definition, for which we had to use a lot of algebra, such as factoring or rationalizing numerators or denominators, or what else? Completing the square here and there, or even special limits from trigonometry that we had to use to get those derivatives. Well, we did a couple of examples in the same way to find the area under the curve by evaluating limits of infinite limits of Riemann sums, right? And it wasn't that pretty. It's all right. It's kind of fun, but it's not the most efficient way to calculate the area under the curve. So now, today we will discuss the fundamental theorem of calculus, which is, well, actually we are going to evaluate the same two integrals we did last time, during the last couple of lectures, but this time we're going to do this basically in a blink of an eye, as opposed to working more than half a page, writing a Riemann sum, turn that into infinite sums in terms of n cubed, etc. We will no longer do that. That took us maybe, what, 15 minutes, 20 minutes each exercise? No, this one is going to take a lot. It's going to be a lot quicker. And I already mentioned these limits of integration before. I mean, again, we are assuming that you haven't seen this before. But I know for sure that some of you took AP Calculus in high school. You know how to do this in using the fundamental theorem of calculus, right? So, or you took this class before. You already know that you have seen it before. But well, this is the first time in which all we're going to do is, so we define a function that should be continuous on the interval a and b. The integral of f of x with respect x from a to b is equal big F, where big F is any antiderivative of f of x. So all we're going to do is find the antiderivative and evaluate that derivative at the upper limit. I mean that antiderivative of the upper limit, and minus evaluate at the lower limit. That's all we're going to do now. All right? And well, there is a pretty cool derivation of where this integral theorem is coming from. However, it's a little too symbolic, and it's a little I don't want to bore you with too many symbols, even though it's pretty fun. So I might do it once we finish the whole section, or once we come back, because I'd rather you guys know how the fundamental theorem works, rather than really where it's coming from. All right? But I think I might do it one way or another, or I will film a separate video about it. Okay? Well, so let's just use the fundamental theorem of calculus to evaluate these couple of integrals. So number one, that's the integral from 0 to 3 of x minus 1 quantity squared. And well, again, if you already took a calculus course, whether in high school or this same course, you know that you can evaluate this integral using the method of substitution. However, we don't know the method of substitution yet. So we will have to go about brute force in this case. That is, expand the binomial. That's the integral from 0 to 3. That's x squared minus 2x plus 1 with respect x, and integrate or find the antiderivative of each term individually. And well, let's recall. In this case, we're going to use the general power rule. Let's recall the general power rule, that is the integral of x to the n with respect x. That's x to the n plus 1 over n plus 1. Well, essentially plus c, but the plus c will not be needed here, and I'll explain why in a minute. So, what we're going to do when integrating these terms is add 1 to the exponent and divide by the new exponent. So add 1 to the exponent 2, that's equal to x cubed over 3 minus 2x to the first power, add 1 to the exponent, that's a 2 over 2, plus the integral of 1 dx, which is just x. And well, in this case, I'm not going to add the plus c. All we're going to do is evaluate this from the lower limit of 0 to 3. Okay? And well, all we do is simply compute f of b minus f of a. And give me a second, I need to plug in my laptop here, otherwise it's going to die. Got it. So, evaluate this antiderivative at the upper limit minus evaluate at the lower limit. However, you might want to simplify this antiderivative just a little bit first, because see how these twos cancel? So this is going to be x cubed over 3 minus x squared plus x from 0 to 3. And well, this is going to be 3 cubed over 3 minus 3 squared plus 3 minus, okay, here's something that it's fine to do, because do you notice how evaluating a c at 0 for all these terms right here is going to give us 0? So in this case, you might want to write down just a big 0. It's fine. You don't need to write down 0 cubed over 3 minus 0 squared plus 0, because everything is going to get just zeroed out when we evaluate it at 0. So that's fine. This notation is acceptable, right? And well, that's 3 cubed, which is 27 over 3. That's a 9 minus 9, and then plus 3. Cancel the 9s. Final answer is 3, which is the same result that we obtained in the previous section using infinite limits of Riemann sums that took forever to compute. All right? In this case, in this case it took me a little more than 1 minute, because I was trying to explain every single step and where is each formula that we're using in this case. All right? So now compare with what you have in your notes from the previous section, you will find out it's exactly the same result. Let's evaluate the second, let's go about letter B. Evaluate also the integral from 0 to 3, x cubed minus 6x, and well, using the general power rule again, add 1 to the exponent, x to the 4, divide by the new exponent, minus 6x squared over 2, and evaluate that from 0 to 3. And well, you might want to simplify the second term, that is 6 divided by 2. That's x to the 4th over 4 minus 3x squared from 0 to 3. And well, that's 3 to the 4 power over 4 minus 3 to the 3 times 3 squared. So that's the evaluation at the upper limit. And the evaluation at the lower limit, again, the same situation as in the previous example. No need to plug it in, because that's going to give us a big 0. You know, evaluate 0 to the 4 over 4, and 3 times 0 squared, that's just going to give us a 0. It's not going to be the case all the time, as we will see in the following exercises. And well, that's going to give us 3 to the 4 power. Is that an 81, I believe? 81 over 4 minus 3 squared, which is 9 times 3, that's 27. And that's 27. I'm going to call this a 27 over 1 because I need least common denominators to compute or to evaluate this difference here. And well, the least common denominator, that's multiply by 4 and divide by 4. So let me do 27 times 4. So 108, right? So that's 81 fourths minus 108 over 4, and that's a negative 27 over 4. All right? That's the same result that we got using that long process of Riemann sums. And do you see how doing it this way, it's a lot quicker? Well, nevertheless, on the final exam, you might be asked to compute one. Maybe not compute the long way because it really takes a lot, especially because on the final exam you would be expected to answer questions because it's going to be cumulative. So most likely at least set up the Riemann sum. But mostly it's evaluating the integrals. So that's our final result. The same number that we got from before using Riemann sums. And again, let's look at letter C, another example. That's the integral from 1 to the natural log of 5 of the 4 e to the x with respect x. Well, so we're going to use another integration formula, another antiderivative formula, in particular, the one that says that the integral of e to the x dx equals simply e to the x. And that's because, well, the derivative of e to the x is itself e to the x. However, we would be expected that its antiderivative likewise would be the same itself. All right, and a potential plus c indeed, right? But again, when we're doing the definite integration, definite integrals, we don't add the plus c. And the reason why we don't add the plus c, check this out. That's because we are adding a plus c, for example, minus another plus c. Those plus c's cancel from the evaluation at the upper value minus the evaluation at the lower value. So that's why we don't write those plus c's. All right. Well, so this is the same as saying 4 times the integral of e to the x from 1 to ln of 5 with respect to x. And well, the integral of e to the x is itself e to the x evaluated from 1 to ln of 5. And don't forget this factor of 4 that I wrote outside. And as usual, just evaluate at the upper limit and evaluate at the lower limit. That's 4 times e to the ln of 5 minus e to the first power. Well, in this case, recall from pre-calculus that e and ln, e to the ln, they're both actually inverse functions, inverse of one another. And in this case, that's going to leave us with 4 times 5 minus e. And you could leave it like this. That's fine. Or distribute, that's a 20 minus 4e. And you might want to leave it in exact form, unless, for example, WebAssign asks you to leave it in a determined number of decimal. Let's say 3 decimal places, 4 decimal places. Well, that'll be upon instructions when we get to WebAssign. So let's look at another example, one more example, and we'll move on to the second part of the fundamental theorem of calculus. So, number 1, let's evaluate the integral of cosine x plus sine x. We're going to use trigonometric ones within the limits pi over 4 to pi over 2. All right? So, let's find the antiderivative of cosine, which in this case is sine, and the antiderivative of sine, which is negative cosine x. And that gets evaluated between pi over 4 to pi over 2. And all we do is, again, evaluate that antiderivative that we obtained at pi over 2 minus evaluate the antiderivative at pi over 4. That's all we do. And in fact, well, doing these Riemann sums with trigonometric functions is just madness. So actually, at our level of mathematics that we're in, we don't have the techniques, we don't have the tools to compute Riemann sums containing these trigonometric functions. So the most you will be asked to do with a trigonometric function and Riemann sum is just set up the Riemann sum, but not evaluate it. All right. So let's see. So this is a sine x. Okay, number one. Let me go over here. Actually, you're gonna need more space. So that's sine pi over 2 minus sine pi over 4. That's the evaluation at the upper limit minus the evaluation at the lower limit. That is sine. Oh, wait a minute. That's a cosine. Actually, that's cosine and pi over 2 minus sine pi over 4 minus cosine pi over 4. All right. So sine pi over 2. Sine pi over 2 isn't that a 1? I think it's 1. 1 minus cosine pi over 2, which is 0, minus sine of pi over 4, I believe that's square root of 2 over 2, and minus cosine pi over 4, which is also root of 2 over 2. Well, all this is going to go to 0, and 1 minus 0 equals to 1. So we are essentially finding the area under the curve, cosine x plus sine x within the interval pi over 4 to pi over 2 in that area equals to 1. So these are a few examples in which we use the fundamental theorem of calculus. We're going to get back to this later when we discuss the method of substitution, which is one of the most critical tools that you need to have a good understanding of it, because Calc 2 next semester relies heavily on this. It's mostly integration next semester. Of course, we're going to go beyond and discuss not just the substitution method, but also partial fractions, trigonometric substitution, trigonometric integrals. Well, it's going to be a really big subject next semester. All right. So, okay. What's the second fundamental theorem of calculus? And guys, by the way, I love this textbook, the textbook that we use for the class. However, there's a few things I disagree with. Not too many in comparison with other books that you know. And one of the things I kind of disagree with our textbook is that the fundamental theorem of calculus that we just discussed, they refer as the second fundamental theorem of calculus, and the one that we're going to do right now, it's actually referred as the first fundamental theorem of calculus, which I don't know why they call this the first fundamental theorem of calculus, and they discuss that first, if it really relies on whatever the second fundamental theorem of calculus is. It's like, I don't know, but I mean, let's see, what about it? So let's consider the integral from 1 to x of the function cosine t with respect to t. One thing to notice here is that the upper limit of integration is a variable. It's not a constant. Okay? So let's simply evaluate this integral. So the integral of cosine t on the x, cosine t dt, that's sine t, rather, because we're integrating with respect to t for now, not with respect to x. And, well, that's evaluated from 1 to x. In other words, evaluate sine x minus sine 1. Whatever that value of sine 1 is, it's most likely going to be a decimal for sure, an irrational number for sure. But we don't care for now. Now let's take the derivative of the result that we just obtained. That is, take the derivative with respect x of sine x minus sine 1, sine of 1. Well, the derivative of sine x, which is cosine x, and the derivative of sine of 1, well, that's just differentiating a constant. Differentiating a constant is just going to give us a 0. And well, the derivative over here is C is just cosine x. And well, let's see if we can find a relation between the result that we obtained here and our original problem. So, notice this cosine x right here, it's the same as this cosine here. I mean, what are we essentially doing? What we're doing here is we are integrating, and then we're taking the derivative again. So what we're trying to say is that the derivative of the integral take us back to the same result once again. And there's a little typo here, by the way. It is from a to x actually, not from a to b, from a to x. So what this tells us is that the derivative of an integral takes us back to the original function. All we do is change the variable that we're using. Well, but you might ask yourselves, why do we do this? Well, number one, because just to denote that these two operators, because these are not functions, these are operators, just the same way like e to the ln, e to the ln x. These are two inverse operators to one another. That's going to give us x, and ln of e to the x equals also x. These are operators that are inverses to one another. In this case, the same way, the derivative, integrate something and then take the derivative, we should get back to the original function. However, why do we need to know this? Because, well, you will use this second fundamental theorem later, well, especially when you get to differential equations, when you're given solutions of these differential equations or potential solutions to test, and in this case given in terms of an integral that we cannot evaluate. Well, so let's see how this works. So this second fundamental theorem of calculus tells us that when we integrate this madness here, take the derivative of it, that's going to take us back to the original function. So in this case, this is our f of t. F of t equals to sine squared t. Our result here should be simply some f of x. But what's f of x? The same function that we have at t, just replaced with an x, which in this case is sine squared x, and that's the result. And by the way, this is the weak form because of the limits of integration go from just a to x. There is a strong form that we will discuss later, and that involves limit that in this case is just something other than x, other than a. You'll see how that works. So, well, right now you don't have the tools to find the antiderivative of sine squared t. Number one, we need trigonometric identities. Well, that we can do to rewrite that integrand right here, and also we need to know the method of substitution in order to compute that integral, which we don't know yet. We haven't gone there yet. But well, again, some of you might already know it, but again, right now we are pretending we don't know that part, so we're gonna go in a different direction. Well, I mean, it's kind of weird how really do we just change the letter? I mean, do we just change the t for an x using the function without integrating? Well, what's going on in the background if you're wondering? Well, so here, this is what's going on essentially. Let me make some space. So we have d dx, that's the integral from 3 to x, sine squared t dt. Okay? Well, notice in this case we don't have to evaluate the integral. We don't have to find the antiderivative at all. And in fact, again, like I mentioned before, we don't have the tools to evaluate the integral, but I'm going to evaluate it in a way. I mean, this is some f of t. So this is d dx. No, I'm not going to have enough space. So d dx of the integral from 3 to x of some function f of t dt. Whatever that is. I don't care what that is, right? I don't care if we can integrate it or if we cannot integrate it. I'm just going to generalize this and say, well, okay, keep the derivative operator. We know that when we have the little f as the integrand, if we integrate that, little f becomes big F of t. All right? Again, by the definition, okay, let me go back to just so you can see what I'm talking about. So, little f becomes big F, regardless of the dummy variable. That could be x, y, z, omega, alpha, gamma, whatever your favorite letter, your favorite symbol, right? That works for everything, every single symbol. So we're turning this little f into big F upon anti-differentiation. That's going to go between the limits 3 and x. All right? Using the first fundamental theorem of calculus, and here is where I disagree with the order. This is the reason why I disagree with the order of the fundamental theorem that the textbooks goes. I mean, because we are essentially using what should have been the first fundamental theorem to go about the second fundamental theorem. I don't know why they have this reverse, but anyway, ddx, and so that's evaluate at the upper limit. That's big F of x minus big F of 3. All right. So take the derivative of big F. Isn't that again little f? We're just going back and forth between little x, find the antiderivative to make it big F, take the derivative again to turn it into little f again. So that's little f, f of x minus, big F of 3, regardless of what this big F is, regardless of what that antiderivative is. So check this out. That antiderivative will be evaluated at some value, at some numerical value, and whatever that expression is, that's going to output a number. And the derivative of a number, isn't it just a 0? Which is just f of x. And in this case, f of x just replaced with sine squared x. That's everything going on in the background. Yes? The answer like that. However, if you're not sure, and if you want to do all this, I'm okay with that. That's fine. And in fact, I think I'm going to do it for the examples on the strong version of it. All right? You'll see how's that going to work. All right. What do we have? Number 2, the integral. The derivative of the integral from x to 2 of tangent cube of 5t. And again, let me tell you guys, we don't have the tools to evaluate that integral, but you guys will have them next semester in calculus 2, sometime after the first month when we get to the methods of integration, that is trigonometric integration. You'll see, it's a lot of fun. Well, one thing I noticed in comparison with the first example is, well, here I have the x as a lower limit and the 2 as the upper limit. Remember those properties of integrals that we discussed last time? We can reverse the order of the integration, but put a negative sign in front of it. All right, that's going to give us simply negative tangent cubed of 5x. That's it. Take the derivative. Well, after we integrate that, take the derivative. That should give us all that. As easy as that. As easy as just changing a t with an x. That's all it is. And just ignore the lower limit, because upon differentiation, that lower limit that gets evaluated at a constant outputs another constant. Take the derivative of a constant. That's just 0. Question? Yeah, good question. So because in this case we have the x at the lower limit and the constant in the upper limit, so we can reverse the order of the limits by having a negative, all right? Negative in front of it. All right, so let's discuss the strong version. All right, the strong version of the second fundamental theorem of calculus, or the strong form rather, instead of having from a to t, in this case, that turns our limits of integration into just any other, your favorite function that you can think of, anything. And well, let's have a look at some example. Well, number one, in this case, that would imply to use the chain rule. And I'm gonna show you the whole process so you can see how this works. Well, in this case, I'd rather do the whole thing instead. So essentially, we have some function h of t, for which again, we don't have the tools to integrate this square root of sine t. I think even with the methods that we have from calculus, it's not possible, well, unless you use power series or the Legbo. You'll see what I'm talking about later. And well, so if this is h of t, that's going to be the integral from 3 to x squared of h of t dt. And well, what is that going to be ultimately? That's going to, so little h is going to become big H. Take the derivative with respect x of big H in the same way that little f became big F, little h becomes big H. H of t, big H of t, evaluated from 3 to x squared. Well, let's do the fundamental theorem of calculus part 1 first. That is, evaluated at the upper limit, evaluated at the lower limit. So this will be d dx of big H evaluated at x squared minus big H evaluated at 3. Well, let's take the derivative individually, d dx of h of x squared minus d dx h of 3. Well, so when we found the antiderivative of little h, that became big H. Now that we're taking the derivative of big H, that's going to become again a little h. H of x squared. However, this is a composite function. See how we have an outermost function, big H, well, that became little h, but we have an inner function, x squared, so we need to use the chain rule to differentiate this properly, multiply by the derivative of the quantity that we have inside of the parentheses, and that is 2x. Minus the derivative, okay, whatever the integral of the square root of t is, it doesn't matter. If we evaluate it at 3, that's going to become just another number, just another constant. Well, the derivative of a constant is 0. And well, little h, which in this case is the square root of sine of, in this case, x squared minus, or times 2x minus 0, and simply let me write down the 2x in front of the radical times sine of x squared. Final answer. Okay? Let's do another example. So, in this situation in which you have to use the stronger form of the second fundamental theorem, I would recommend that you do all this process, because in this case it's not just as easy as replacing t with an x, because in this case we're replacing it with an x squared, but in this case we would need to differentiate that quantity we evaluated with. Unless you can, it's still possible to go from here to there in one shot, as long as you know what you're doing, that you know that you're plugging in that whatever that function is, but times its derivative. But again, my advice, I would do this whole process. Let's go about one more example here. So that's the derivative of the integral from x to 2. Wait a minute. Hold on. I didn't change the exercise. So let me make something up. I thought I had something already. Never mind then. Okay. So let me do d dx times the integral from sine x to maybe let me make it interesting. E to the x cubed of the square root of 1 plus ln of x. Oh, t actually. dt. All right. So that's the example that I'd rather make up in this case because, well, I don't know what happened here. So number one, make this our h of t. That will be d dx of the integral from sine x to e to the x cubed of h of t dt. Well, it doesn't matter. Whatever h of t is, integrate little h, turn it into big H of t, and use the first fundamental theorem to evaluate that from sine x to e to the x cubed. Okay, so that'll be d dx of big H of the upper limit, which is e to the x cubed, minus big H of sine x. All right? So let's take the derivative of these two terms. Number one, let me distribute the differential operator here, the derivative operator, d dx of h of e to the x cubed minus d dx, of big H of sine x. Well, upon differentiation, big F, which initially was little h, is going to become once again little h. So little h of e to the x cubed. However, this is a composite function, so we need to use the chain rule. So that's going to be the derivative of h times the derivative of the inside. And the derivative of the exponential will be itself e to the x cubed. But we still have more composition. We still need to differentiate, multiply by the derivative of what we have in the exponent, which is 3x squared. And then minus differentiate big H to turn it into little h of sine. But what's the derivative of sine that we need to multiply by? With that? Derivative of sine? Cosine. And we're essentially done with the calculus here. So all we have to do is go back to the original function f of h of t, replace it with e to the x, so 1 plus ln of the upper function e to the x cubed times this madness here, e to the x cubed times 3x squared, which is the derivative of that, minus the square root of 1 plus ln of sine x times cosine x. And we're essentially done, but how about we simplify this a little bit? Number one, on the one hand, see how this ln cancels the exponential, leaving us only with the x cubed. And I would rather have this written the following way: 3x squared e to the x cubed times the square root of 1 plus x cubed minus cosine x square root of 1 plus ln of sine. And we're done.